Welcome to the HEOR Insights YouTube channel. In this explainer, we're going to break down Markov models. These are an absolutely essential tool in health economics and outcomes research, especially when we need to model the way chronic diseases progress over long periods of time. We've got 5 key areas to cover. First, we'll ask why do we even need Markov models? Then, we'll dive into their 3 core components. After that, we'll see exactly how the model runs, step by step. Next, we'll get into the math of calculating transition probabilities. And finally, we'll look at how these models are actually used in HEOR and for health technology assessments. All right, so let's start with Section 1. Why do we need Markov models in the first place? Well, it really comes down to the shortcomings of simpler approaches when we're dealing with complex diseases. Now, a tool like a decision tree is great for modeling acute conditions, things that happen over a short, straight path. But for chronic diseases, they just don't cut it. Think about it. Patients can have recurring events. They can move back and forth between being healthy and sick over many, many years. A decision tree's rigid, one-way structure can't handle that. And that's exactly where Markov models come in. They are built with a cyclical structure that's perfect for simulating these complex, long-term health journeys. Okay, moving on to Section 2. Let's look at the 3 fundamental building blocks, the architectural blueprint, if you will, of any Markov model. So the single most important concept to grasp is what's known as the Markov assumption, or memorylessness. What this really means is that the model has no memory of the past. So a patient who has been in a sick state for 5 years has the exact same chance of moving to another state as a patient who just entered that sick state in this cycle. Now, clinically, that's a huge limitation, right? And we'll talk about some clever ways to address this later on.
The first core component is the health states. You can think of these as the different buckets a patient can be in at any given time. For a simple model, you might have states like healthy, sick, and dead.
Now, these health states have to follow a few strict rules. First, they have to be mutually exclusive. A patient can only be in one state at a time. Second, they need to be collectively exhaustive, meaning you've covered all possible scenarios for the patient. And finally, you'll always have at least one absorbing state like death, which is a one-way door. Once a patient enters that state, they can't leave. The second component is the cycle length. This is basically the tick-tock of your model's clock. It's the set period of time over which things happen. You might choose 1 year for a slowly progressing disease, or maybe 1 month for something that changes more rapidly. Just know there's a trade-off. Shorter cycles are more precise, but they also require a lot more computing power. And the third and final core component is transition probabilities. These are the engines of the model. They define the chance of a patient moving from any one state to any other state during a single cycle. We organize these in a grid called a transition matrix, and the key rule is that for any starting state, the probabilities of all possible moves, including staying put, must add up to exactly 1. So we have our 3 components: states, cycles, and probabilities. Now in Section 3, let's see how they all work together to actually run a simulation. The whole thing runs in a simple 4-step loop, repeated over and over. Step 1 is initialization. You place your entire cohort of patients into a starting state, usually 100% in healthy. Step 2 is transition. You apply your transition probabilities, which moves percentages of the cohort into different states. Step 3 is accrual. For this cycle, you calculate and assign the costs and the outcomes, like quality-adjusted life years, for the patients in each state. And Step 4 is just repetition. The model takes the new distribution of patients and does the whole thing again for the next cycle. The main output you get from all this is something called a Markov trace. It's a table, just like this one, that shows you exactly what proportion of your patient cohort is in each health state for every single cycle of the model. It gives you a really powerful, dynamic picture of how the disease progresses and how an intervention might change that progression over time. All right, let's move on to Section 4 and dig into the math a little bit. Calculating the transition probabilities correctly is absolutely critical for your model to be accurate, and it's something that often comes up in technical interviews. First things first, we have to be crystal clear on the difference between a rate and a probability. They are not the same thing, and you can't use them interchangeably. A rate, like a hazard rate from a clinical trial, is an instantaneous measure that can technically go from 0 to infinity. A probability, on the other hand, is the actual likelihood of something happening over a defined period, like your cycle length, and it's always stuck between 0 and 1. So we often need to convert between these values, and there are 2 formulas you absolutely have to know.
To turn a rate into a probability, you use the formula p equals 1 minus e to the power of negative RT. To correctly adjust a probability for a different cycle length, say from an annual one to a monthly one, use this formula here. A really common mistake is to just divide the annual probability by 12. Don't do it. It's mathematically wrong and will cause you to overestimate the risk.
Okay, for our final section, let's connect all this theory to the real world. How do we use these models for things like submissions to health technology assessment or HTA bodies, and how do we address their built-in limitations?
Remember that big memorylessness problem we talked about earlier? Well, modelers have a really clever technique to work around it called tunnel states. These are basically a series of temporary states that you create to help the model keep track of how long a patient has been in a certain condition. So, for example, instead of having just one big sick bucket, you can create a sequence: sick year 1, sick year 2, sick year 3, and so on. This structure allows you to apply different transition probabilities for each of those years. So the risk of dying might be much higher in sick year 3 than it was in sick year 1, which is often a much more accurate reflection of what happens clinically. Another key refinement that you'll almost always see is the half-cycle correction. You see, basic models assume everyone transitions right at the very end of a cycle, which isn't quite right and can skew your cost and quality results. This correction adjusts for the more realistic assumption that, on average, transitions happen about halfway through the cycle. It's a small tweak that improves the model's accuracy.
So, where do we see these models in action? Well, they're the absolute workhorse for cost-utility analyses that get sent to HTA bodies like NICE in the UK or CADTH in Canada. They're what generate the CALIs used to calculate ICERs. They're also used for budget impact analyses and are standard in complex areas like oncology, modeling states like progression-free and progressed disease, and cardiovascular disease.
So I'll leave you with a question to consider for your own work. When you're building a new model from scratch, which of these two big limitations do you think is more critical to address first? The model's inherent memorylessness, or the timing of when transitions happen within a cycle? It's a key practical question that modelers have to weigh on every project.